Hello, ladies and gentlemen. I am Dr. Claudia Albers, Planet X researcher and professional physicist, and today I'd like to bring to you another one of my articles. This one I have just written. It is entitled The Darkening Sun. There is now overwhelming evidence of many thousands of objects being close to the Sun and exchanging plasma with it. Figure 1 shows one of these smaller objects. These objects are found in the Sun's corona and are about the size of the Earth. As you can clearly see, this is a three-dimensional object. The Sun's corona seems to be in the foreground. It has a bright spot in the center. It has a surrounding area which is darker. And you can see that it looks three-dimensional, so that the white spot seems to be further out from the Sun's corona or closer to the camera. There's also a faint line around the object. It's irregular shaped, which indicates plasma closely surrounding the object. And this plasma is about the same color as the Sun's corona. It is probably plasma from the Sun's corona that this object has gathered around itself. Then in figure 2, we see another one of these objects. It seems to have a plasma ejection. As you can see, it's in the shape of a Birkeland current, so it goes out and then out towards the right and then connects again, out towards the right, connects again. And here it's either connecting directly to the Sun or there's another object there which may actually be further into the Sun's corona. It does seem to be brighter than this object here. So they may be connecting to each other, but they are known as well to directly draw plasma from the Sun. There was one caught in 2012 doing just that. Now, it is well known that white dwarfs draw plasma from the Sun, so it's not surprising that these objects, which are basically cool down white dwarfs, would do the same. And most of the white dwarfs that have been studied are about the same size as the Earth, so these objects are right in line with that size. But now it must be clear that these objects cannot be planets. Planets would not survive in the Sun's corona because the Sun's corona is at a temperature of between 1 and 3 million Kelvin. And at that temperature, a rocky planet or even a gas giant planet would liquefy and then turn into plasma, and it would be absorbed by the Sun's corona, therefore. But these objects go through the red giant phase. They are actually stars. They start out as main sequence stars. They become what are called now stellar cores. And they do this because when they start losing some energy, they start expanding, going into the red giant phase, letting go of the outer layers of gas. Eventually they become a white dwarf where they have let go of almost all the gas, which then forms an irregularly shaped cloud. They are left with a core and an envelope of material around the core. And this material is not spherically shaped, it's toroidal in shape, and I'll talk about that some more. Then we have the larger stellar cores. Not all of them are Earth-sized. This one is about a third of the size of the Sun. This has been independently observed from two different places on Earth, by two different individuals, by Scott and by someone in Germany. And this image is from July 26. You can see it still has some material attached to its surface. It has a solid surface. We can see that because it has grooves in it. And this object is connecting to the Sun and is drawing plasma from the Sun. You can see this is the Sun's corona, the plasma in it, and we see plasma being drawn from the Sun's corona towards the object and gathering around the object. And it's denser in this region here. And then we see that the object is ionizing its own material, and that material is being exchanged with the Sun. Now, the reason why this happens is because these objects connect to the Sun magnetically. These are, again, what are called stellar cores. So that's what remains from a star after it's shed most of its layers or surrounding material, gas. So we can see this material does not actually look gaseous, but when it's ionized, well, it's not doesn't look gaseous when it's attached to the surface, but when it's ionized, it looks cloudy. It's actually a plasma. These objects then, therefore, would eventually let go of almost all the layers of gas. They would be left with an envelope. In this one actually has very little of that material left and attached to its surface, which would have been part of its envelope. And eventually, they become a white dwarf. A white dwarf is initially very bright and hot, but it cools down and eventually is not only able to emit infrared radiation, which is the state that these objects seem to be in when they come into the solar system. However, after a little while of being in the solar system, they are able to start emitting light, and this is why we see some of these smaller ones having bright centers. Now, the way these objects connect magnetically to the sun and, as we will see, to each other is through their magnetic fields. So these objects have very strong magnetic fields. They draw out the sun's magnetic field, and which is then represented by these magnetic field lines. Then the sun's particles would spiral along the outgoing magnetic field lines towards the object, and this object's ionized particles would spiral along the returning magnetic field lines to the sun. And the magnetic field lines have to, of course, form closed loops. Now here we see a very interesting object. As you can see, we have a bright core in the center, and we have darker cores surrounding that core. But these are very symmetrically distributed around the central one. And the central one would have been the one that's been in the sun's corona longer. It has gained more energy, and these ones would have had less energy. They're not able to emit light from the core yet. That's why they are dark. And so, as we can see, they attach to each other as well as to the sun. Also, this shape and the way they attach to each other is very interesting. So this is illustrated in this figure. So this would be one of the dark core stellar cores. This is the front view where we see through the hole in the cloud. The cloud is shaped in this manner. It's toroidal in shape. And we see the core on either side. It's dark, and this is when the object has gained enough energy so that it can emit light from the core. It's basically the same thing, although this envelope may actually grow and decrease in size. It may be small when the object enters the solar system, and then it grows because it gathers more of this envelope from the sun. Then the way the objects that we saw in figure 5 were attached to each other was this way. So they attached on the sides of the object, and they at regular spaces from each other. So they form this very symmetric shape. And if we were to look at it from the side, this is what it would look like. So we don't see an object attaching itself so it's on top here. They're on the sides. And this is very interesting. This shows us that they're not connecting gravitationally, because gravitation, the gravitational field is spherically symmetrical. And so an object could attach itself to any point on the side of the sphere without any problem. So we would get an irregular pattern. But here we get a very specific, very irregular pattern. It shows that the magnetic field and therefore the force that is causing these objects to attach, is causing them to attract each other, is toroidal, has a toroidal symmetry. So here we have some examples. This is the spherical symmetry. Any point on the side of this object is at the same distance from the center, that is at the same distance from the center, would have exactly the same attractive force. because the gravitational force is spherically symmetrical. But the magnetic force is not spherically symmetrical. It's toroidal. And the reason why, we can see it here, if we have a current flowing in this shape, then we would get a magnetic field that is toroidal in shape. So we would have a current flowing along a ring, and then we would get the result of that would be a magnetic field that is toroidal in shape. It forms the cylindrical shape around the center, and further out, larger rings, and in the center it forms the sort of magnetic field associated with a bar magnet. And in fact, it seems that the solar system also exhibits this toroidal symmetry, because all the planets are orbiting close to the ecliptic, and that also shows that they are attaching to the sun along the same lines as these objects are attaching to each other. In other words, along an ecliptic line, and therefore not exhibiting a spherical symmetry that we would expect from the gravitational interaction. Then furthermore, I think I needed to mention the fact that I've been observing the sun jolting. And if the sun is the center of the solar system and all the planets are attaching to it, be it through the gravitational interaction or the much more likely magnetic interaction, because we see this toroidal symmetry in the solar system. But if they were just attached to the sun, if the sun were to move, the planets would move with it at the same time. So we would never be able to observe the sun movement or moving. And I have been observing it jolting since October. And what does that show? That shows that the sun is no longer the central object of the solar system. The central object that's producing the central force that's attracting all the planets to that center. So the sun would be a strong producer of magnetic field, but it's not the sole one anymore. There are other objects, these stellar cores, in the center of the solar system that are also producing magnetic fields. And it seems that now the planets are attached to the group, not just to the sun. And therefore, when the sun moves in response to these other objects, we are able to observe that from Earth. Then here in this image, we have the large blue stellar object again. This is from May 12, 2017, so one of the telescopic images that Scott took. As you can see, it too exhibits this toroidal symmetry in the pattern of the stripes of the material attached to the surface. And this material is what it ionizes and then exchanges with the sun. We can see this cloud where it seems to be doing just that with the sun. And on the May 26 images, it has a lot less of this material. It's obviously given it to the sun, whilst it has gained plasma from the sun. So we see this kind of toroidal symmetry in the fact that it has these stripes. So the material always gathers along this area of the object, which is in a plane perpendicular to the axis of the object. So this is the plane perpendicular to that. This would be the ecliptic plane for this object. Then here we have some more images. There are two of these objects here. This is the larger one. The smaller one has a bright center, and it obviously has plasma, and it looks like part of the corona, but it's detached from the corona. And that shows that these objects gather plasma from the sun's corona around themselves. This one seems to be not just one, but two. There's one with a bright core, and there's another one with a dark core. So it's starting to form a cluster, and that would be, it will probably next gather some more objects, and they too will form this symmetrical shape with four around the central core. again attach themselves along the plane perpendicular to the axis of the central object. And then we have here in figure 10 an image of the Sun in 17.1 nanometers. It's an SDO image, so provided by the Solar Dynamics Observatory satellite. This is from August 7th, and we see the Sunspot group, which was called AR2665. It's now, I think, called 2670 because it's gone through another pass facing the Earth. So it's its second pass. It had very strong CMEs. There was particularly a very strong one on July 23rd. And at that time, there was an object seen close to the sunspot and the CME. But now we see this area around the sunspot group that is much darker than the rest of the Sun. Some of the darkness around the Sun is caused by coronal holes. However, this area is not a coronal hole. It's actually plasma in the Sun that is not emitting as much light in this wavelength or is as bright in this wavelength as the rest of the surface of the Sun. And that is significant as well. That suggests that the Sun has gained some material from one of these stellar cores, and it gathered around here. And this material does not emit as much light as the Sun's own plasma. Obviously, it has less energy. So this is the object that we saw on July 23rd, 2017. It was huge, and it was actually a little larger than the Sun itself. So it's not surprising that if there was an exchange of particles between the Sun and this object, that it led to the Sun gathering so much darker material at that time. And of course, the object was close to the sunspot group, so it's not surprising that the material gathered in that area. And it's probable that this object may actually have had something to do with the strength of that CME because it was unexpectedly strong. And of course, because these objects pull on the Sun's magnetic field, it's likely that that will increase the strength of the CMEs because the plasma from the Sun is more easily accelerated outwards. So here is, again, that dark material. In conclusion, smaller Earth-sized stellar cores surround themselves with plasma from the Sun's corona, as well as immerse themselves in the Sun's corona. Some emit light from the core, and some have dark cores. And also they cluster together or connect to each other magnetically as well as to the Sun, and thus seem to absorb energy from each other. These objects, as well as the solar system, conform to a toroidal symmetry expected of a magnetic interaction, and I should add not expected, of a gravitational interaction. The Sun jolting shows that it is no longer the sole central magnetic field producer in the solar system, and then the dark region around the Sun is an indication of a huge particle transfer in which the Sun received a large amount of particles from a large stellar core, and is an indication that the Sun can get much darker very quickly. This is Dr. Claudia Albers, Planet X physicist. Thank you for watching.